The U-boat will decide the outcome of the war. This is what Hitler is telling the Germans, as his underwater sailors harvest victory after victory in the Battle of the Atlantic. Every German is told his submarines threaten the entire Allied war effort with collapse. Germany rejoices in the news that if the United States and Great Britain continue losing at sea, they will be defeated everywhere.
They had a broaching problem on torpedoes during World War II. They'd actually enter the water and then broach. So they built the variable angle launcher down there, which is a huge device where they could take a full-size torpedo as well as aircraft launched torpedoes and impact the water, and they could control the angle and velocity for water entry.
And now, hedgehogs and SeaHawks and rats. Submarines were already old news by the second decade of the 20th century. They weren't new, but they were rapidly becoming a whole new class of threat. Effective, terrifying, and damn difficult to keep track of. By the opening of World War II, anti-submarine warfare, ASW, was, of necessity, becoming an essential discipline. Shield lines of destroyers were deployed to escort convoys, and significant resources of the secret weapon war were aimed at finding and neutralizing the ever-elusive U-boat. Once you had a way to find it, the best bet was to engage the submarine at long range. But guns were only good on the surface. And long-range torpedoes were big, heavy, and not very reliable. Rockets could get depth bombs out away from the ship. And retro rockets could go after whatever you hunted up with your MAD gear. The wartime rocket R&D effort that spawned Knott's China Lake wasn't the only secret weapon program being run by Caltech. Right in the middle of Pasadena, and in several spots in the surrounding countryside, Caltech pursued new torpedoes for the Navy, anti-submarine rockets, and everything to go with them. As the war wound down, and post-war planning pointed toward maintaining a complete West Coast Ordnance R&D establishment, Knott's became a two-side activity, with rockets and air weapons centered at China Lake, and underwater ordnance at the Pasadena Annex, Knott's, PA. Pasadena had Green Street and the Foothill Plant, Morris Dam facilities, and the Eden Canyon activities that had spawned the China Lake Pilot Plant. Some wartime facilities were closed or returned to civilian use, but Knott's Pasadena would fast grow to include specialized T&E and support facilities at San Clemente Island, San Nicolas Island, and Long Beach, along with strange ranges and strange boats and barges. For many years known also as P-80, Knott's Pasadena was a unique, complete RDT&E activity in its own right. PA pioneered system simulation and integration, silent, slick torpedo designs, and underwater T&E technologies. Combining Knott's PA's underwater ordnance expertise with the air and surface weapon mastery of the High Desert Rocketeers made for the Navy's premier all-weapon RDT&E activity, with deep sea and arid desert ranges adapted to support the cutting edge of anti-submarine warfare endeavor. As the submarine's offensive potential evolved, anti-submarine warfare, detection and destruction gained ever-increasing priority. And as the direst threat of the lurking submarine evolved from the interdiction of essential supplies to the incineration of entire cities, anti-submarine warfare gained a prominent place in the Cold War and a high priority in the station's efforts to protect the fleet and the nation. Knots concentrated on the lightweight, multi-purpose torpedoes that could be launched from small ships or air-delivered, or rocket-launched to engage an enemy sub well outside its own weapons range. Centered at Pasadena, the station's torpedo development program produced the EX-2A, predecessor of the Mark 44, and the surface-launched active acoustic Mark 32. Knots contributed to the Mark 41 and 43 torpedoes, small active acoustic weapons with air and rocket launch capabilities, and to the Mark 44 and Mark 46 systems, advanced medium-range acoustic weapons deliverable from almost any platform, including rockets, helos, and drones. Along with simulation and survivability studies of the long-range, wire-guided, nuclear-tipped Astar. With retorque, Knots advanced the technology of torpedoes, made them slicker and faster using swish, and made them quieter and more accurate with revel. Knots also developed REFIC, a simplified advanced ASW fire control system, and supported Dash, the drone anti-submarine helicopter that entered service in 1963 and returned to China Lake in the 80s as a missile target. By the late 1940s, the station's increasingly sophisticated rocket-fired sub-smashers had outpaced the wartime Hedgehogs and flying milk bottles. From a new rocket motor and a high-tech fiberglass-cased depth bomb, Knots made weapon-able, with its oddly familiar trainable launcher. More advanced was the rocket-assisted torpedo, the Rat, with tag-on launch rails adaptable to most any destroyer. Rat quickly gave way to the more sophisticated ASROC, short for, obviously, anti-submarine rocket. ASROC, with an advanced fire control system, hit the fleet in 1961, in its familiar box launcher, carrying a Mark 44 torpedo. Demands for more capability and better range led Knots to launch ASROC from Terrier rails, upgrade to a Mark 46 torpedo, add a nuclear depth bomb option, and to pursue LASROC and ERA and eventually VLASROC, the vertical launch ASROC. VLA allows for any aspect launch from long distances to deliver an advanced torpedo. Some other activities tried a more complicated approach to flying a torpedo, but it's ASROC that's still in the air 50 years on. Alongside rocket-launched torpedoes and depth bombs, the station pursued families of submarine-killing rockets, air and surface-launched, as well as sub-to-sub. The station participated in the nuclear ASW programs of the era as well, testing and integrating Lulu and Betty, and trainers for those. The sub-launched sub-killer Subrock, testing and improving it with track, air, surface, and subsurface launches. And the atomic option for ATSROC, for when a single torpedo just wouldn't do. RAT and ASROC and Weapon A are practically common parlance compared to the lesser-known litany of Knots ASW projects, from ACTAR and ANU and ASTER, CLASP and Clinker, through DASH and Deep Dunk and Derry, FATUP, Fulham and Hydra, LOSS, PUFS, Moray, and to some extent Rocksight, Sailor Hat, SCAT, SeaHawk, SOSUS, Star, and Stone, not to mention Subad, Subic, Sus, and Swish, and at least one edgy project that evidently needed an Aztec to pronounce. There were facilities like VAT and VAL, and the Star Range. Curve, the robot claw machine, was related, although Pop-Up and Pea-Shooter and Fishhook and other Polaris facilities belonged to another episode. More than the torpedoes, more than the rockets, the station contributed to some very secret aspects of some very public projects, and maintained an active program in fleet ASW data analysis. China Lake and Pasadena worked on SeaHawk, the advanced ASW ship concept, and participated in the Hydra and Sailor Hat studies to determine the effects of nuclear detonations on ships and aircraft and ASW weapons. And the station directed the development of SCAT, a hedgehog-delivered noisemaker designed to bell the cat, as it were. China Lake's Moray mini-sub was conceived as a sub-hunting stealth fighter. Although it only saw research use, the concept was well demonstrated. And Knott studied the development of undersea facilities that might support sonar picket lines along foreign coasts and serve as bases for those mini-sub fighters. The technology base for advancing ASW was given high priority too. Knott's scientists and their associates became experts in acoustics and signatures and surface effects and the ways echoes operate. They studied silent motors and boundary layer control and the slickness of fish, as well as the very composition of the ocean, and water mass and sound transmissivity and ocean currents and gravity anomalies, and even bioluminescence, to see if the tiny creatures that glow when they're disturbed might show up a sneaking submarine. Knott studied and applied submarine hydrodynamics, torpedo hydrodynamics, dolphin hydrodynamics, and magnetohydrodynamics. Yes, even Flipper had potential ASW application. Although the station was split in 1967, with the Pasadena Annex and the ASW mission going to San Diego as part of what would become NOSC, Knotts had already written several chapters in the Manual of Anti-Submarine Warfare. And mission purification aside, China Lake would continue to support a variety of ASW systems, like Subroc-cum-Sea Lance, and vertical launch versions of some station standards. With the end of the Cold War, the submarine would maintain a more subtle deterrent role and continue as a silent protector of the fleet, among other things. But the post-Cold War world has also brought the possibility that even the more primitive of the so-called rogue states might be able to mount a shattering offensive. And in a world where even drug runners have adopted the cast-offs of the Cold War, ASW remains a top priority mission, and the silent, secretive submarine remains a potent player for defense, deception, diplomacy, and deterrence. But that's another story.
In the early years of World War II, Allied shipping suffered heavy losses. In 1942, these losses amounted to over 1,600 ships, almost 8 million tons. Most of these were victims of Axis submarines. There was an urgent need for an air weapon for use in anti-submarine warfare. Depth charges and the newly developed retro rockets were used with some success against the submerged craft. But the 30 caliber machine guns on the aircraft were no match for the deck guns of the enemy. The history of rocketry and anti-submarine warfare changed abruptly in the spring of 1943. This was the result of some tactical experiments conducted by the British. They had replaced the explosive warheads on the 3-inch fin-stabilized rockets with heads of solid steel. The result was impressive. By June 3rd, there were 9 verified kills of German submarines with this non-explosive weapon. On June 7, 1943, Admiral Ernest King, Commander-in-Chief of the Navy, gave instructions to advance the work on a Navy anti-submarine rocket for service use as soon as possible. One result of this order was the abrupt shift of a surface rocket project being developed by the California Institute of Technology at Pasadena, California, to the development of an air-launched anti-submarine weapon. Initial experimental work was done with British rockets. A Navy pilot, accompanied by a group of Caltech scientists, conducted the first tests at Goldstone Range, a dry lake bed on the Mojave Desert. Much of the experimental work of this period is typified by the revisions that were made to the launcher design. The British design was a rail 90 inches long. This length was supposed to give the rocket an accurate start on its way to the target. A practical remedy was to shorten the rails to 70 inches. It was found that this did not affect the accuracy. Successively, more and more of the launcher was snipped off until the zero-length launcher evolved. This launcher merely used 2 posts. There was no significant loss of aiming accuracy, and there was a great reduction in drag. The rockets could be fired in singles, pairs, or in salvo. In submarine attacks, the general practice was to fire in pairs. Further ground tests were conducted using a large paper submarine as a target. They were successful. Water entry tests were run at the Salton Sea. By August 1943, the Navy requested the production at Caltech of 10,000 rockets a month. This marked the beginning of the first large-scale rocket production in the United States, and within a month after the project started, deliveries began. One of the first employments of the 3.5-inch forward-firing rocket was aboard the small aircraft carrier Mission Bay in the latter part of 1943. Lieutenant Habich, the aviation ordnance officer, reported,
"The Germans got the picture pretty fast, that they couldn't stay up on the surface, because we didn't have to get so close as we did with the depth charge. It reversed the trend in submarine warfare and gave us an advantage."
The rocket served admirably throughout the war as an effective anti-submarine weapon. In 1943, in the upper Mojave Desert, important construction activity began. Admiral King's order, which had initiated the 3.5 rocket program, also provided the justification for the construction of a much-needed proving ground for aviation ordnance, the U.S. Naval Ordnance Test Station. In subsequent years, this would become the Navy's largest weapon research and development facility. The Naval Weapons Center.
War II, one of the few facilities available for development work on underwater missiles was the fixed-angle launcher, located at the Morris Dam torpedo ranges. This launcher fired missiles by compressed air and proved valuable in tests of aircraft torpedoes. However, since the water entry angle of a missile affects its underwater performance, the fixed-angle launcher was seriously limited in its use. Engineers in the newly formed Underwater Ordnance Department realized the need for a new kind of launcher, one which could fire many types of air-to-water missiles from a variety of firing angles at velocities up to supersonic, a facility which could fully document the progress of these missiles from launcher through water entry and underwater travel. The design conceived for the proposed variable angle launcher called for 2 barges to be spanned by a 95-foot bridge which would support the water end of a launching bridge. The launching bridge was designed for possible installation of as many as 6 300-foot launching tubes, varying in diameter from 12 to 48 inches. The upper end of the bridge would rest on a movable carriage. On the opposite side of the launching bridge, a counterweight car would balance the launcher and carriage. To adjust the launching angle between 0 and 40 degrees, a motor drive was to be constructed which would act on the 16 2 1/8 inch cables connecting the carriage and counterweight car. Plans also called for a well-instrumented range consisting of 3 general side view cameras placed at intervals parallel to the 1,000-yard range, a movable camera car, 2 rear view cameras, and an overhead camera. In addition, 24 hydrophones, or underwater microphones, would record the missile's underwater travel. Construction of the variable angle launcher was started in early 1946. The launcher site selected was a slope on the south side of the Morris Dam Peninsula, naturally inclined at a 45-degree angle. Clearance of the entire site was rapidly undertaken, and soon the steel-reinforced concrete ramps which would support the launcher carriage on one side and the counterweight car on the other were underway. Over 40,000 sacks of cement were used in the grouting operation to stabilize the underlying rock, and 2,000 yards of concrete were poured to make the 4-foot-thick launcher slab. While the slab was being prepared, the 35 by 60 by 12-foot special pontoons which would support the water end of the launching bridge were brought in over the winding mountain roads to the dam. Upstream from the launching site, the pontoons were joined by an all-welded connecting bridge which would ultimately support the water end of the launcher. Once the slab was prepared, the rails for the carriage were laid. These rails are about 10 times the weight of standard mainline railroad track, weighing 1,200 pounds per yard. As construction of the south slope progressed, the opposite slope of the launcher was being prepared. Rails to support the counterweight car were a standard heavy rail section. The counterweight car, which rides on 10 pair of railroad wheels, was made with a steel frame and reinforced concrete body, acting together structurally as a composite member. Its 500-ton weight was obtained by incorporating steel punchings and other scrap in the concrete in place of rock aggregate, and by filling the car compartments with pig iron. One of the biggest jobs to accomplish was the assembly of the 300-foot-long bridge, the longest all-welded bridge ever constructed in the United States. The bridge, the 22.5-inch tube, and the tank to provide high-pressure air for launching missiles were assembled upstream at a convenient level assembly area on the shore of the lake. The lake level was brought up to transfer the bridge load from the assembly area to the pontoons, and then, supported partially by the pontoons and partially by a barge, the bridge was floated downstream to the launcher site where it was accurately positioned over the carriage. The lake was then lowered until a large pivot pin under the bridge engaged in the carriage. The launching tube is supported at 25-foot intervals by adjustable turnbuckles, which permit its accurate alignment. Above the slopes and supporting the upper portion of the inclined tracks is a concrete cellular building with 7 floor levels, housing electronic control and recording equipment and other apparatus. To complete the VAL construction, the housing and the main drive machinery were raised to the top of the concrete structure. There, the 16 wire cables were laid over the 3-drum hoist and connected at either end to the launching bridge and the counterweight car. The variable angle launcher, including auxiliary equipment and instrumentation, was completed in May 1948 at a cost of approximately $2 million. After a brief dedication ceremony, the launcher was christened by a single firing of the torpedo Mark 13 from the 22.5-inch launching tube. The need for a variable angle launcher had increased during the months of building. Thus, almost immediately following the dedication ceremony, the VAL was put to use. A typical test usually begins with adjustment of the launching angle. Movement shown here is about 50 times faster than normal. Once the launching angle is set, the work of preparing the instrumentation and the test missile begins. Personnel line up the flare and side view cameras in the camera car. The overhead camera is fed out on its cable until it is directly over the water entry point. 3 general side view cameras along the west shore, a general rear view camera atop the concrete structure, and a rear view camera beneath the launcher muzzle give full above water camera coverage. Meanwhile, the missile to be launched is moved out of the nearby torpedo shop, where it has been loaded with instruments for recording roll, pitch, and yaw of the missile during its run. The range is clear. The arming plug is inserted. The control operator makes his final checks. 7, 6, 5, 4, 3, 2, 1, fire! Let's take that again slowly. A 1/10 of a second after firing, compressed air rushes into the tube behind the torpedo, pushing the missile down the tube as electronic devices measure its velocity and acceleration. As soon as the missile leaves the tube, its behavior is recorded in many ways. Flares attached to the missile's tail make this pattern on film. Thus, the missile's speed, path, water entry deceleration, and whip can now be calculated. These pictures were taken by one of the 3 general side view cameras. This was taken by the water entry side view camera. This by the overhead camera. A picture from the rear view, and one from the tower showing the wake. A record is even made of underwater travel. By locating the holes in these nets, the first trajectory points are plotted. Those explosions are delay squibs set off in the head of the missile and picked up and amplified by hydrophones. A recording oscillograph in the concrete structure gives accurate data for plotting the missile's underwater path. Since completion in 1948, about 2,000 launchings have been made from the VAL, some at velocities exceeding 1,000 feet per second. Its versatility has affected great savings in time and cost in the development of torpedoes, rockets, depth charges, bombs, and mines. A tool of research, development, and test, the variable angle launcher and its well-instrumented range has proved its value many times, serving a unique purpose by making possible better underwater weapons for the use of the Navy.
was that?
LTE Thompson, Dr. Tommy to one and all, was one of those most responsible for the early success, indeed the post-war survival, of the Naval Ordnance Test Station. Hand-picked at the highest level to be the first technical director of knots, Dr. Tommy set the standard for laboratory leadership and military-civilian cooperation. He knitted together often estranged academic and military cultures to establish China Lake as a laboratory and as a community. While his namesake laboratory may not be much of a lab these days, it was once a unique and creative proposition, as was Dr. Tommy. Well before knots, LTE Thompson was noted for his work primarily at Dahlgren in ballistics, rockets, naval guns, propellants, and ammunition, including the Thompson formula for armor penetration. He was a collaborator of Robert Goddard, father of American rocketry, and of Deke Parsons and Charlie Lauritsen, influencing the Manhattan Project along with the development of the China Lake Lab. The driving force behind the radical knots principles of operation, Thompson helped ensure technical leadership for the technical staff and RDT&E programs, with a measure of organizational freedom and individual responsibility unique to China Lake as a military organization. Remembered with great respect and great fondness by civilians and military alike, Dr. Tommy's subtle brilliance is at the heart of the China Lake corporate culture, and he set much of the lab's course for decades to come.
At the Naval Ordnance Test Station Annex in Pasadena, management immediately set out to learn just how much was involved in the task assignment's brief statement, engineer the Mark 32 for production. To explore their problem in detail, they dispatched a liaison man to Key West, Florida, to witness and report on OpDev 4 evaluation tests of the few Mod O's left over from World War II. Another man met with the future manufacturers of the torpedo, the Philco Corporation in Philadelphia, to discuss the design and production problems. And back at Thompson Lab, daily contact was initiated with the MA and RE divisions of the Bureau so that their guidelines could be followed. Top men in electronics and acoustics, structures, propulsion, controls, and ballistics met to study these guidelines and appraise the performance requirements. Staff engineers pored through early torpedo manuals and dissected the Mod O with the thoroughness of Swiss watchmakers. Classes were held to share information. Yes, we were learning. We learned that the Mark 32 was an active acoustic torpedo, which could search for and pursue quiet submarines. It was designed to be launched from surface vessels or by aircraft, to attack submarines lying motionless or traveling at speeds up to 12 knots in depths from 60 to 500 feet. When the torpedo enters the water, it sinks to an 18-foot depth before the propulsion motor starts. The torpedo then begins a downward spiral at a fixed dive angle of 3 degrees in a 280-foot circle. The torpedo is constantly transmitting pings in its search for the target. A 600-yard acoustic range enables it to detect a submarine within an area of 36 city blocks. Here's the target submarine as seen from above. And this is an overhead view of the torpedo radiating pings as it circles downward in search of the target. When echoes are received by the torpedo, it breaks away from its helical search and starts into an arc of a pursuit circle. When echoes are no longer received by the torpedo, it returns to its search circle until it finds the target again. These on-off turns are repeated, leading the torpedo in a weaving path toward the target. Yes, this is what the Mark 32 Mod-O was supposed to do. But in a coded conversation from Key West, our liaison engineer told a different story. A story of what the torpedo was doing in the evaluation tests at Key West. When the 32 was air-launched, the shock of water entry frequently damaged the pendulum assembly, deformed the rudder and elevator linkage rods, and broke the motor supports. Furthermore, timing of the programmer was irregular due to a varying battery voltage and slipping cams. And pressure switches were fouled by dirt and salt. Well, there it was. Our liaison man had pinpointed the design weaknesses in the Mod-O. But these were not the only problems. We soon found that equipment for testing and aligning the torpedo was inadequate. The exercise heads were unreliable. Furthermore, in the 5 years since World War II, many of the torpedo parts which did function properly were no longer being manufactured. And so now, for the first time, we face the reality that the Mod-O, with its component weaknesses, failures, and obsolescence, would not be ready for production engineering until its deficiencies could be corrected. Pressed by an early completion deadline, Knott's management directed the engineering effort towards improving the performance and reliability of the Mark 32. These improvements marked the beginning of the Mod 1. Meanwhile, Philco, under pressure from the Bureau to get the hardware out the door, tackled the production problems of acceptable Mod-O components until the parts being redesigned by Knott's would be ready. At Knott's, redesign went along on schedule. In the weeks to come, hundreds of drawings went into the station shops, to the foundry for castings, then to the machine shops, to the slotter, to the mill, to the drill press, to the lathe. And soon, the designs became parts, and the parts were assembled into components for laboratory testing. Later, in the mechanical evaluation lab, the pendulum was tested on the drop table, a machine which simulates the shock of water entry. Drops like this cause damage to linkage pins. And so, back to the drawing board to limit the swing of the pendulum and test again. And this time, there was no damage from shock. Then, in the hydrodynamic simulator lab, optimum feedback control of the pendulum circuit was determined. The simulator is invaluable for reproducing torpedo motion during underwater travel. And then, 60 miles off the coast of California, at the Navy San Clemente Island, the first aircraft launchings of the prototype torpedo were undertaken. Film coverage was provided by cameras installed on the high cliffs. Tests like this helped to prove out the redesign, bringing the Mark 32 closer to completion. Simultaneous with component testing, putting the 32 on paper became an important part of the program. This mass of technical information was to serve not only as a report to the Bureau and as training aids for new engineers, but also as guides for the manufacturers. To cover the redesign, it took more than 3,000 drawings, several hundred specifications, and dozens of reports. These publications showed the progressive phases in the torpedo's development, how the Mark 32 Mod-O became Mod 1, and later Mod 2. The Mark 32 Mod 2 was dropped from many different kinds of aircraft. This F-6F, for instance, carries one torpedo under each wing. Here, the torpedo is being loaded into the bomb bay of a TBM, where steel slings attached to the bomb rack support the torpedo. It can also be launched from blimps. At the height of the evaluation program, as many as 40 runs a week were made, with about half of these airdrops. And so, our evaluation and later evaluation by OpDev 4 established that the Mark 32 Mod 2 is particularly effective as a weapon of opportunity during the prosecution of a Hedgehog or depth charge attack. The Mark 32 Mod 2, under tactical conditions, has a hit probability of 30% when launched from fixed-wing aircraft and 60% when launched by blimp. And as a surface-launched weapon, it has a hit probability of 50%. Proved and accepted, the torpedo Mark 32 has been delivered to the fleet, another weapon for the defense of America.
Condition yellow exists. This will be a firing run.
Welcome aboard the USS De Haven. In a few minutes, you will see highlights from the Bureau of Ordnance evaluation of the RAT anti-submarine weapon system. But first, we of the Naval Ordnance Test Station would like to express our appreciation of the splendid cooperation received from the bureaus, shipyards, forces afloat, and contractors. It was this cooperation which made it possible for the Naval Ordnance Test Station to complete the development and commence the evaluation of the RAT weapon system on January 17, 1957, a date which was scheduled more than a year ago. We're ready for a firing run now. You can see better from the 01 deck, so I'll transfer you up there.
Greetings from the 01 deck. And now, before the firing, a few words by way of orientation. Behind us is San Clemente Island, our base of operations, some 60 miles off the coast of California. And there on the fantail of the destroyer is the RAT launcher, mounted piggyback on the aft twin 5-inch gun mount. We will be seeing more of the launcher later. As you probably know, the RAT missile is a rocket-thrown torpedo. During the early days of the program, we called it rocket-assisted torpedo, hence the code name RAT. A rocket throws an acoustic homing torpedo to the area of the target submarine. At a preset time in the missile's flight, the rocket is separated from the torpedo, and the torpedo is then parachute stabilized for the remainder of its flight to water.
Condition ready, Chris. This is a firing run.
And now, firing time has arrived. There is no countdown, so watch for the opening of the launcher door, which indicates the standby to fire. Flash bulbs on the launcher show instant to firing for data purposes. And now the door is opening. And this is the RAT. And now, may I introduce the Naval Ordnance Test Station engineer in charge of the evaluation. Could you tell us, what is the main purpose or objective of the evaluation?
Well, there are several. The principal objective of the evaluation is to determine how well the RAT weapon system meets the design and performance specifications. There are, by the way, 4 principal components of this system: the detection, the fire control, the launcher, and the missile.
Now, in making an attack, the sequence of operation of these 4 RAT weapon components is best shown in a sketch. Let this line represent the surface of the water. Here is the destroyer, and down here is the target submarine. Now, a sonar dome protruding from the hull of the ship and operated as part of the SQS-4 sonar gear transmits pings out to various ranges up to 15,000 yards. On contacting a target, the pings are reflected back to the sound dome and passed on to the sonar console, which furnishes range and bearing of the target to the attack director. The attack director computes the factors which will permit accurate firing of the missile and passes this data on to the stabilization computer. The computer corrects this data in terms of ship's motion and passes it on to the gun mounters. The firing switch is then thrown, energizing the rocket igniter and firing the RAT missile. At the predetermined time, separation takes place. Then, 2 parachute stabilizers deploy in order. By the time the torpedo enters the water and begins its port helical search pattern, the target has reached a position where torpedo acquisition is probable. The mount is released and trained in the direction of the target submarine, and the chase is on.
Wait a minute, wait one. Okay, I'm ready. He's ready. He's ready. Ready? Red standby. Red standby. Fire rat. Fire rat.
Sonar, Mach 53, missile away. Sonar. Radar 3 locked on. Water entry.
Somewhere out there, the target submarine is attempting to evade RAT's payload. Below in the target submarine, the sonar operator listens to the on-off attack of the active acoustic torpedo. As he reports the torpedo's bearing, the crew maneuver the sub through an evasive course in an attempt to escape. Sonar reports the torpedo's closing, and a radical change in course is made. They're taking her deeper to escape, but too late. It's a hit.
Raven, this is Lobo. Kilo, kilo, kilo.
Well, that's about how these firings went during our 6 weeks at sea. But with the completion of the Bureau of Ordnance evaluation of the RAT weapon system, it was concluded that it is an effective and workable anti-submarine weapon. When tabulated, the final score showed that of 47 single firings, 40 4/10% were hits.
What is that doing there?
As most things at China Lake go, the airplane on the traffic circle hasn't been there all that long. Switzer Circle was graced with its Skyhawk on sticks in the spring of 1969. just in time for Armed Forces Day. The little Skyhawk is in many ways emblematic of the evolution of Navy aviation and of the China Lake Laboratory. Designed early in the jet age and introduced in 1956, the simple, rugged A-4D could fit on the smallest carriers and serve as a one-weapon, one-way atomic bomber. The A-4 became a top-flight tactical asset and a superb smart bomber, taking Shrike and Walleye from range to reality. China Lake modified its Skyhawks into nosy birds for in-flight missile simulation, built them into test beds for its pioneering ejection seats, mounted them with experimental fire control systems, and dropped, fired, and lofted from them just about anything imaginable. The display bird is significant itself. The third production aircraft built by Douglas, it was part of the evaluation testing of the original fleet model, and its multiple stores of Snake Eye and Rock Eye, a typical combat load in 1969, are perhaps the best known of China Lake's I family of freefalls. The last production A-4, an A-4M, arrived at Armitage Field in 1980, bedecked with the flags of the Skyhawk's Allied nation users. The simple, reliable analog airplane served right up through the early days of the digital age, as essential in the lab and on the range as it had been in combat.
Needed was an ASW weapon system capable of detecting, identifying, tracking, and destroying a submerged target submarine. A weapon that could be launched from a standard submarine torpedo tube at tactically useful depths. As of this test firing, the need for such a weapon system was nearing fulfillment. Subrock, a submarine-launched anti-submarine rocket, was in its 5th and final year of development and testing. The Naval Ordnance Test Station's role in this vital weapon program has been to furnish technical assistance and conduct a series of developmental and evaluation tests at the San Clemente Island Sea Range and the desert facility at China Lake. In mid-December of 1958, subrock tests began on the Knott's ground ranges at China Lake with a series of motor separation tests on the supersonic research track, SNORT. Similar high-speed runs were made to evaluate subrock's inertial guidance package under various acceleration loadings. Extensive ground ranges at China Lake provide missile flight distances up to 26 miles. Ground-to-ground launchings of subrock from a Terrier launching system proved out the weapon's ballistics, as well as the boost and total guidance phase. Data gathered during each event were quickly reduced and analyzed. Handling the different kinds of sub-rock data was simplified by the use of the Knots-developed data reduction system called NODAC. This system simultaneously converts different kinds of analog data into digital form for use in the IBM Computer 7094. By early 1960, enough data had been gathered on the land-based tests to begin underwater launch tests of the weapon. In anticipation of this phase of the sub-rock test and evaluation program, a test site had been readied at the Knots San Clemente Island Sea Range. Few sea ranges in the free world could have provided a more suitable site for these upcoming tests. Steep cliffs provide excellent sites for camera coverage of missile trajectories. Deep waters allow submarine operations close inshore, while shallow water areas with flat, sandy bottoms simplify missile recovery. The climate permits year-round operations. In preparation for the first phase of underwater testing, Knots developed a special launching system to fire sub-rock from a fixed underwater launcher. Once the umbilical connection was made, the launcher was lowered to the ocean bottom. The transition to underwater was aided by scuba divers who checked the system for air leaks and ascertained that all cables cleared the LCU. The surface of the ocean is an intangible water-air interface without substance or thickness, yet penetrating it has been costly both in manpower and in time. When operational, sub-rock not only would have to emerge from the sea, but effect the transition back into the sea. In this first test, sub-rock successfully demonstrated its ability to emerge from the sea. As planned, a thrust reversal and separation system was initiated shortly after water exit to terminate the missile's flight. Now, with numerous successful underwater launchings from the fixed launcher behind it, sub-rock was ready for its final proofing, the launching from a fully manned submerged submarine. With the arrival of the USS Permit at the Long Beach Naval Shipyard, this final phase of the sub-rock technical evaluation program got underway.
Stand by one. Stand by one. By one. Eject orders. Eject. 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33.
The first successful launching of the sub-rock weapon from a submerged submarine took place at the San Clemente Island Sea Range on March 28, 1963. During the following months of test and evaluation, sub-rock continued to demonstrate its operational capabilities, and by December of 1963, when the Knots technical testing was completed, the weapon system was ready for evaluation by the Operational Tests and Evaluation Force scheduled for mid-1964. Knots is proud of the support it has been privileged to give toward the successful development of the sub-rock weapon system.
The drag of a full-scale torpedo has been reduced 26% by the ejection of additive fluid into the boundary layer. The test vehicle, carrying 4 gallons of pre-mixed additive solution, ejects the fluid at the rate of 1 gallon per second. Swept back along the skin surface of the fast-moving vehicle, the fluid mixes with the ambient water, causing what appears to be a damping of boundary layer turbulence. Of the more than 25 different additives studied either in a pipe flow or disc facility, the 2 additives that have been found to be the most effective in reducing friction are guar gum and polyethylene oxide. Here, a solution of the additive polyethylene oxide is prepared for a cableway test. The additive concentration is 0.2%. The fluid will be ejected from the test vehicle at the rate of 1 gallon per second for 4 seconds. After 20 seconds of run time, when the test vehicle has reached a constant velocity of 55 feet per second, fluid ejection will begin. The sudden increase in the turbine RPM that occurs when the additive fluid is first ejected demonstrates the almost instantaneous reduction in drag. The change in velocity was approximately 10 feet per second. Currently, practical application techniques are under study.
Dolphins have long been credited with unusually high speeds, speeds that appear to conflict with known hydrodynamic principles. Accordingly, studies of dolphin locomotion were recently undertaken for the Navy by the Naval Ordnance Test Station, Pasadena. The objective was to establish exact measurements of top speeds, power output, and drag of dolphins, and determine whether the dolphins use phenomena that would be of use to the Navy. In the spring of 1960, the Naval Ordnance Test Station purchased Nottie, a 5-year-old female Pacific white-sided dolphin. Early training for the upcoming hydrodynamic tests consisted of teaching Nottie to coast through hoops in preparation for measuring the drag or retarding force. Other training consisted of wearing a drag collar for measuring power output. Later, in a 315-foot towing tank at Convair in San Diego, Nottie was trained for speed runs. Although Nottie looks extremely fast, top speed was only 15 knots, following a 2-second acceleration period. Maximum power output, measured during acceleration and from speed runs wearing a collar, was 2.1 horsepower, about the same as a human athlete for a 5-second period. Body and tail movements were appreciable during acceleration, but the speed, drag, and power results showed nothing unusual. A reason might be because the Pacific white-sided dolphin is a slow species. Or perhaps no exceptional results were achieved because the tank was too small, or because Nottie had been confined in a small area prior to the tests. Or, for reasons known only to herself, Nottie hadn't really tried to swim at top speed. Questions like these and others would be explored for answers in future tests with other dolphins under more ocean-like conditions and using different training methods. A final check of the speed of dolphins was made in the Whalers Cove tank at Sea Life Park, where 2 Pacific spotted dolphins and 4 spinner dolphins were trained to swim at high speeds around a small island. The speeds appeared to be unusually high. Speed data were taken using a camera. The speed was found to be 16 knots after about a 3-second time elapse from the start. Again, nothing hydrodynamically unusual was found. It is known that dolphins are assisted in locomotion by swimming near a ship or in large waves. This could account for some of the unusual speed reports that have been made. We have learned much about dolphins, and new knowledge will continue to accumulate. But unless new and unusual speed data are obtained using calibrated equipment, it is likely that dolphins exhibit no exceptional hydrodynamic capability.
Project SeaHawk is an analytical study intended to result in a new class of ASW ship. The project's prime objective is a significant increase in ASW effectiveness. Part of the Knott's Pasadena technical effort in the project is a simulation analysis of the ASW weapon subsystems. The purpose of the analysis is to determine if and how the effectiveness of the weapon subsystem can be increased, what standard should be used to measure the increase, and the magnitude of the increase. An additional aspect of the analysis will be to explore the weapon expenditure rate against false targets and the ship exchange rate. That is, the ratio of SeaHawk ships lost to enemy submarines destroyed, two crucial factors in anti-submarine warfare. In utilizing simulation techniques, computers in effect become own ship, the target submarines, the environment, and the ASW weapon subsystems. To determine the various systems' limitations when coping with more than one target, two target submarines having dynamic and acoustic characteristics similar to the skipjack and the thresher will be used. Environment limitations such as ray path distortions due to refraction, ocean bottom, and sea state will be built in. When completed, the ASW weapon subsystem simulation analysis will aid in defining the requirements of the components necessary to achieve an increase in effectiveness and provide a quantitative estimate of the increased kill probability of a weapon subsystem using the components. High-speed, deep-diving submarine targets impose severe performance requirements on conventional torpedo detection systems. To improve the torpedo's capabilities to detect and classify the advanced submarine, ultra-high-speed data processing techniques need to be applied. Correlation detection is an application of such a technique. Targets are located and classified by continuously comparing in minute detail the received signal with a coded signal that was transmitted. A parallel magnetostrictive delay line correlator called the White House correlator, under development at Knott's, permits the required millions of calculations per second to be performed within the severe space and weight limitations imposed on a torpedo homing panel. The experimental work required to develop and optimize the homing system is being accomplished by the use of data digitally recorded at sea. Transducers mounted on a movable platform are lowered to depths up to 600 feet. Echoes from different classes of submarines operating under a variety of conditions are recorded on tape by electronic equipment housed in a portable van. This high-speed oscilloscope presentation of a run of the submarine USS Permit illustrates the progress being made. The graph superimposed over the presentation permits determination of both target velocity and range. The USS Permit, operating at periscope depth, is approaching